product of 3 gamma matrices, which means nu and rho here are antisymmetric. I can move that over to the covariant derivatives. So this is actually can be rewritten as a commutator of 2 covariant derivatives. Commutator of 2 covariant derivatives, basically using parallel transport, gives you the Riemann tensor. So it's very cute. Even if I'm doing fermions over here, basically I'm doing standard GR manipulations. That's the Riemann tensor. Now I have 3 index gamma over here, 2 index gamma over here. I have a product of 5 gamma matrices with the appropriate antisymmetrization. If you play with the appropriate identities, you can rewrite this term over here into something like that. In fact, this is just the Einstein tensor. So let me just pull out the Einstein tensor over here. I have psi bar mu gamma mu epsilon, which I can buy around a flip. You go like that. So if you look at that, that's the Einstein tensor up here. That's the Einstein tensor here. This actual minus sign. You add them together, you get 0. So in fact, the supergravity Lagrangian is invariant under supersymmetry transformations, as a must. Now, just a slight note of caution. If I actually do a variation over here of the spin 3/2 direct equation, I just said, oh, I'm going to vary psi over here. The metric is hiding. The Veer bind is hiding inside gamma matrices. There's a spin connection. There's metric stuff inside the covariant derivative, which means if I actually vary this, I actually have to vary the bosonic parts inside here as well. So it gives me sort of 4 Fermi type terms. And so demonstrating full locus limit supersymmetry beyond the linearized level is more of a challenge. And there's other ways to deal with that. But at least as an overview, we see how supersymmetry works at the supergravity level. Yeah.
Can I ask a silly question? So, since the lowest order supergravity action is already invariant under the supersymmetry transformation, what's the motivation of adding more terms? I think in your previous slides, you're saying that it's just a very special case.
Yeah. The problem is the lowest order Lagrangian is actually not invariant under supersymmetry. And where it's not invariant is, I did not write down the supersymmetry variations of the bosonic parts of the graviton parts over here. And so this term is the lowest order delta Lagrangian F. There's additional stuff over here which I didn't write down. And so this additional stuff over here needs more terms in Lagrangian to cancel. And you start building it up until the whole thing becomes supersymmetric.
Okay, when you mean lowest order, you mean lowest order in what?
Well, here I mean 2 Fermi, this variation of delta psi is a boson with a parameter epsilon.
Right.
So this down here is a 1 Fermi term, 1 fermion. I can also get a 3 fermion term over here. So it's the lowest order number of fermions. Good. Which just goes to show that some of the supergravity stuff is a little bit complicated. Yeah.
The previous lecturer explained that general relativity is the unique low energy Poincare invariance theory of spin 2 particles. And I wonder there is something similar statement about the supergravity.
I think the answer is yes, but I don't really know the answer to that. Certainly the Einstein part. No, that's a very good question, right? So we know this is the unique sort of nonlinear part of gravity over here, it's an Einstein-Hilbert term. And I believe when you supersymmetrize that, this ends up basically being unique. Now you can add additional fields. So you have to say what's your starting point. And the starting point is 1 graviton, 1 gravitino, supersymmetrized. Is that unique? And I think the answer is yes.
In Westrumino models, Lagrangian seems to have 2 bosons and 1 fermion. How to
count things? Oh, perfect. Yeah, we can count. Let me go back to the Westrumino Lagrangian here. Majorana. First of all, let's count the scalars. These are real scalars. So there's two real scalars, so I call that 2 real degrees of freedom. Now the fermion over here is a 4 real component fermion. So you might worry, there's 2 real scalar degrees of freedom, and there's 4 fermionic objects over here. However, the fermion satisfies the first order Dirac equation, which relates 2 of the fermion components to the other 2. So the Majorana fermion actually has 2 real degrees of freedom. And I can also understand that on shell, that this is spin 1/2. So it has 2 helicity states, plus 1/2 and minus 1/2. This is spin 0, and so there's 2 spin 0 states over here, and 1 helicity 1/2, 1 helicity minus 1/2 state over here. So it's 2 plus 2 on shell degrees of freedom.
Does those color appears due to the chirality?
I'm sorry?
Should those colors
Oh, the pseudo scalar.
appear for the chirality?
Well,
Why
well,
does
yeah,
we consider the Schutz color?
Yeah, the standard way of doing, well, this is uncharged, as I wrote it over here, and this is a non-chiral theory. But I can certainly go into the charged case, where I'll write this as a complex scalar, 1 complex scalar, and 1 Weyl fermion. And the counting is the same. The Weyl fermion is a 2 complex component fermion. When I go on shell, that reduces that to sort of 1 complex degree of freedom, and then I have 1 complex scalar degree of freedom as well. Now you might ask a little bit, what happens in the sort of more general case when I don't impose any Dirac equation, and then I end up with, well let's keep it in the Majorana notation. I have two scalar degrees of freedom, and I have 4 fermion components over here. 2 bosons, 4 fermions don't match. I add what's called an auxiliary field, F term, and I have real and imaginary parts of F. So I have real and imaginary scalar, real and imaginary F. I have 4 bosonic degrees of freedom and 4 fermionic degrees of freedom over here. So it's 4 plus 4 off shell, 2 plus 2 on shell. So it's just a snapshot or a quick overview of n equals 1, sort of simple supersymmetry in 4 dimensions, where I showed sort of the global case, like the Wezumino model, and the n equals 1 supergravity. One thing we can actually do is extend the supersymmetry algebra. And so instead of having 1 spinor supercharged, I have more than 1. So I introduce an index I over here, which runs from 1 to capital N. And so I can introduce what's called n extended supersymmetry, or I can have capital N supercharges, each one having 4 spinor components. And so the standard algebra is QQ gives you a translation or a momentum generator over here. Now I introduce a delta Ij, so Q1 gives you momentum, Q2 gives you momentum, and so on. However, once I do that, I can also have additional terms on the right-hand side of the algebra. C is just a charge conjugation matrix, that's not important. What I have is X and Y. I did not write down commutators of X and Y, because X and Y commutes with all the other generators that are known as central charges. And this theory over here basically has 4n real supersymmetry components. So 4n sort of real supercharges. And what I talked about before was n equals 1, basically. Now, I won't go through representation theory of this, but just to state that because I have a more complicated right-hand side of the algebra, if the central charges are not equal to 0, I can end up with fancier representations. And typically I got massless representations, n equals 0. I can have long representations, mass is bigger than the central charge. Or I can have short representations, or semi-short, semi-long, things like that, where mass is equal to central charge. Obviously, central charge is a matrix, so this is a bit of a simplification for n equals 2, this is basically what you have. Now, this is very interesting. If I have the central charge turned on, then unitary representations demands mass is bigger than or equal to the central charge, and this is saturation of the bound, n equals z over here. This is known as the BPS limit, or the BPS bound, or supersymmetric bound. Let me just focus on massless representations, since that's usually a good starting place over here. So this is the same table as I wrote down before, where I've labeled helicity states over here. The numbers here are the number of helicity states. So n equals 1 is what I had before. This is when I erase the gravitational multiplet, and you just see this pattern over here. N equals 2 extended supersymmetry. The cleanest one is to see is this 1, 2, 1 over here is just the binomial coefficients. And I start at helicity 2, down to helicity 1, that's the graviton. I can also ignore the gravitational multiplet. You can have a vector multiplet, and you can have a hypermultiplet or hypermatter, like that. The more supersymmetries I have, the bigger these representations get in terms of how many helicity states are connected to each other. N equals 1 basically connects 2 helicities differing by 1/2. N equals 2 connects 2 helicities differing by 0, 1/2, and 1 units, like that. N equals 4, you can imagine, connects 5 helicity states, and 1, 4, 6, 4, 1 are the standard binomial coefficients. It's not a mystery why that emerges in terms of the Clifford algebra. But one thing that's interesting is because I need to have helicities that differ from 2 units from the highest to the lowest helicity over here, I have, at a minimum, helicity 1 or spin 1. So I have n equals 4 vector multiplets. I do not have n equals 1 so-called matter multiplets without having a vector field. So it's not easy to hear about like n equals 4 superradian mils. N equals 4 superradian mils has a lot of nice features to it. One thing is, from this over here, vector multiplets is all you have. You can't have sort of like obvious sort of matter like quarks or something like that. If you go to n equals 8, then you have to connect helicities differing by 4 units. So I start at helicity 2, I can generate all the way down to helicity minus 2, and these are just the binomial coefficients for 2 to the 8. So when I get to n equals 8 supersymmetry, I'm left with only spin 2 or graviton multiplet. This shows you that n equals 8 is basically a supergravity theory. You can't do n equals 8 without gravity. It just doesn't fit. And if I try to go beyond n equals 8, then all these helicity states have to sort of push beyond helicity 2 or spin 2. So another statement here of what I said before is if you demand spins or helicities, massless spins less than equal to 2, then the maximum supersymmetry you could have is n equals 8 in 4 dimensions. So it's a bound on the number of supercharges you can have. N equals 8 is 32 real supercharges. Now, the other thing you can do, so I talked about extending supersymmetry by adding more supercharges, adding more generators to the algebra. Another thing you can start imagining to do, especially as a string theorist, is to go up in dimensions. I started with 4-dimensional supersymmetry, go about 5, 6, 7, and so on. Well, here's a complication you don't really see in a non-supersymmetric theory. It's that fermions are very different, or could be very different in different dimensions. Yeah, Dirac fermions, Weil fermions, Majorana fermions, Weil. And whether you can impose these sort of Majorana conditions or chirality Weil conditions depends on the dimension you're in. It's usually mod 8. And so it's not so easy to write down sort of one universal dimension independent version of supersymmetry. Usually the different superalgebras, the different supersymmetric theories you write down are dimension dependent. They share overall features, but the details depend on what kind of spinners you have in that kind of dimension. However, there's still a universal property. I can try to count on-shell degrees of freedom for massless degrees of freedom here, and you still want number of bosons equal to number of fermions. So just give simple examples. A real scalar has 1 degree of freedom in capital D dimensions. A vector, a massless vector with gauge invariance has transverse degrees of freedom, so it's D minus 2. If I have an n-form potential, then I have something like that. The d-dimensional graviton has something like that. So these are basically simple powers of the dimension d. On the other hand, spinors, you need to come up with a representation of gamma matrices in d dimensions. And the way to do that is you can build them up out of Pauli matrices, or there's other tricks to build them up. You find out that the basic feature of spinors is they grow as 2 to the d over 2. That's the 4 or the integer part of d over 2. And so as I go up in dimensions over here, I get 2 to the d over 2, which can start getting very large over here. So if I want to match bosons and fermions, these go as some power of d, these go as some exponential of d. Pretty soon when d gets big, you can't match bosons and fermions anymore. And so if I limit myself again to the maximum spin 2, you find out the highest dimension I can go is 11. This incidentally is 1 time 10 space. If I have more than 1 time dimension, I can go to 12. But anyway, so just from matching bosons and fermions, you find out that the highest dimension you can go to is 11-dimensional supergravity. So 11-dimensional supergravity is kind of fun. For extended supersymmetry, it's probably the easiest theory to write out. It's not that easy to write out, but it's actually, compared to other lower dimensions, probably the tidiest theory. This also shows up in M theory, so it's really useful to sketch that a little bit. The basic supersymmetry, supergravity, should have a metric, should have a graviton and a gravitino. So sure enough, there's a graviton, there's a gravitino, and this is on-shell degrees of freedom. The gravitino has 128 sort of Bilstein states in 11 dimensions. You can see that's 2 to the 7, good powers of 2, something like that. Metric has 44. Bosons and fermions don't match unless you introduce what's called a 3-form potential over here. So this is a 3-index antisymmetric tensor. It has a 4-form field strength, just like F mu nu equals d mu a nu minus d mu a nu for the maximum field. I can have another derivative over here, so F equals dA basically. If you count on-shell degrees of freedom, 84. 44 plus 84 is equal to 128. So everything matches up very nicely. So again, I want to go right down to lowest order terms. Otherwise, it's a little bit more complicated than this, but this is a snapshot. So the supergravity Lagrangian lowest order fits in 3 lines. Actually, on a sheet of paper, they can fit into 2 lines or something like that. And it's not too bad. I have 3 fields over here. Each field has to have its own kinetic term. So here's the Einstein covariant action for the metric. The 3-form potential has an F squared term. This is a 4-index F defined like that. And the gravitino has the standard sort of Rudolph-Schwinger spin 3/2 Dirac equation over here. Now there are some interaction terms. The next line is very interesting. This is FFA term over here, which can be written a little bit more geometrically as F wedge A. And then over here is a Pauli-like coupling. It has the gravitino over here with F over here. So basically, free Lagrangian plus coupling, something like that. And if you actually worked out the 11-dimensional supergravity algebra, you find 32 real supercharges. That's the same counting as the n equals 8 theory in 4 dimensions. And in fact, 128 plus 128 degrees of freedom is also the same as the n equals 8 theory in 4 dimensions. So this is at least a very strong hint that these 2 theories should be related. 11-dimensional supergravity and n equals 8 in 4 dimensions ought to be related to each other. And in fact, that's certainly true. If you take this theory over here and reduce the 7-dimensional torus, which I'll highlight a little bit tomorrow. Well, the reduction idea I'll highlight tomorrow. I won't actually do the 7 torus since that's a little bit messy. then you'll find out that I can actually reduce this long-dimensional theory, this long-dimensional Lagrangian, into the Lagrangian for n equals 8 supergravity in 4 dimensions. Well, let me just give you this cute little table over here, which is, if I think about the possibility of extending supersymmetries, instead of, so I wrote down on the horizontal side the number of real supercharges you have, or extending the number of dimensions, which is the vertical axis over here, you can create a table of sort of what can you have in sort of standard supersymmetry or supergravity type theories. Let me just highlight this horizontal line over here. In 4 dimensions, I talked about n equals 1 theory. But then you can also have the extended theories all the way 2, 3, 4, 5, 6. I did not write down n equals 7, because if you have n equals 7, you actually have n equals 8 in disguise. And then it goes up to maximum spin 2 is n equals 8. I also talked about going up in dimensions, and you have 11-dimensional supergravity. That's sort of a unique supergravity in 11 dimensions. M is sort of referring to it as M theory. And so that's 11-dimensional supergravity up here. Now, when I have a table like that, the idea is, well, maybe I can actually move around in this table. And if I start with this, and I compactify on a torus, I can compactify from 11 to 10 dimensions, I get 2A theory. I compactify down to 9 dimensions, I get these various theories. I compactify on a 7 torus, I get n equals 8 in 4 dimensions. So I can move up and down over here by torus compactifications. In order to move sideways over here, I have to reduce the number of supersymmetries. You can do that with Calabi-Yau compactifications or more non-trivial compactifications, which usually move you more diagonally down this table as well. So let me just give you a little bit of a preview of what I'll talk about a little bit more tomorrow.
Just one question. About this table, in d equal 5, there is no n equal 1. So there is a theorem.
It depends on what you, another way to think about this table is on defining what the capital N means. And so there's always some ambiguity in this capital N labeling. And some people will call this n equals 1. Most people call this n equals 2. What it is the question is, what's the minimum spinner in 5 dimensions? And 5-dimensional spinners are kind of like 4-dimensional spinners plus a gamma 5 matrix. You can extend an even-dimensional Clifford algebra into an odd one just by having the gamma 5 type matrix. However, by introducing the gamma 5 matrix, in a way you can't just keep a Majorana condition and extend that into 5 dimensions. So you don't have a 5-dimensional Majorana spinner. So the minimum spinner in 5 dimensions is a Dirac spinner, which is the 8-component spinner. So I can say my minimal supersymmetry here is 1 Dirac spinner, call it n equals 1. Or I can also use the language that, well, I don't have a Majorana spinner, but I can have a pair of what's called symplectic Majorana spinners, which means I can't really pull it apart. But I can just sort of label 2 4-component spinners in 5 dimensions. It has to be an even number. And because I have 2 4-component spinners, I call it n equals 2. Now another promotion of why it's nice to call this n equals 2 is because if I go vertically, n equals 2 and 5, it is the same n equals 2 and 4. But this is why I like to, in some sense, I don't really like this notation. The better notation is the numbers up here. You just say how many real supercharges there are in your theory, and then there's no ambiguity. Similarly, 6-dimensional theory, 1, 0. Some people call this 2, 0. It's very confusing. So there's differences in notation, but the point is, once I specify a number of supercharges, then it's determined. Good. So I just want to give you a brief preview of compactification or torus or circle reductions, which I'll say a little bit more about tomorrow. But to say, if I had a higher dimensional field, I can split my space-time into sort of two sets of coordinates, call it x mu and yi. And the idea is x mu are going to be my lower dimensional coordinates, and my yi are going to be my torus or internal type coordinates. And I took my 11-dimensional field, so phi here is meant to be just a generic 11-dimensional field, and I say I make it independent of my torus or my internal coordinates, make it dependent only on my lower dimensional x mu fields. I've basically implemented a simple torus reduction. So I have my 11-dimensional space-time over here. I break it up into sort of 11 minus n dimensions times a n torus over here with my lower dimensional coordinates x mu, my torus coordinates yi. So I make all my fields independent of the torus coordinates. That's very simple. The other thing I realize is if I have tensor fields as opposed to scalars, they carry 11-dimensional indices. So my 11-dimensional metric has what I call capital M and N indices. Those are 11-dimensional indices. But 11-dimensional indices can either be sitting in the lower dimension or in the torus or higher dimension over here. So using the same mu and I labels, and the 11-dimensional metric can break up into components that are lower dimensional G mu nu metric. They can have one lower, one higher dimensional G mu I, or two internal coordinates Gij. Now from a lower dimensional point of view, Gij, this does not transform as a lower dimensional tensor. I and j are internal indices. They are not affected by lower dimensional Lorentz transformation. So this looks like a scalar in 4 dimensions, or in lower dimensions. This transforms with a mu index as a vector. This transforms as a rank 2 tensor. Likewise, the free-form potential can have indices sitting in internal or external spaces like that as well. Now, A, M, and P needs to be antisymmetric. It's an antisymmetric tensor. So we look at A, I, J, K, for example. If I reduce on a circle at a single internal index, and they call it 11 for like x11 direction or something like that, then having 3 internal indices means I have to have index 11, 11, and 11. That's the only internal index I have. I need to antisymmetrize that. It doesn't work. So A, I, J, K, 3 antisymmetric indices only starts working when I have a 3-dimensional torus, basically. Then it becomes A, 9, 10, 11, something like that. Likewise in space-time, if I go to 2 low dimensions, then these things over here don't antisymmetrize as well. So let me just take a baby step, which is to take 11-dimensional supergravity, reduce 1 dimension to 10 dimensions. Turns out that gives me 2A supergravity, or non-chiral supergravity in 10 dimensions. There's 2 maximal supergravities in 10. There's the chiral 2B and the non-chiral 2A. It should be obvious when you're going from an odd dimensional non-chiral theory and you go down in a circle, you're not going to generate chirality, so it has to give you the non-chiral. Okay. As I said, the internal index is basically just 11. So I can break the metric up into G mu nu, G mu 11, and G 11, 11. And the free-form potential, A mu nu rho, or A mu nu 11, basically. I can group that in a little bit more elegant way by taking the 11-dimensional metric and writing it as ds10 squared. The ds10 squared over here is telling you G mu nu is the 10-dimensional metric over here. My 11th dimension, I just call y over here. So G11, 11 is basically the coefficient of dy squared, which is e to the 4/3 phi. There's a reason these factors are chosen as they are, but nevertheless, the point is this is G11, 11 is basically giving you phi. And then if I actually expand this out over here, that's a one-form C, which is basically a vector field. And this C1 over here is basically a form way of writing G mu 11. Likewise, in a form notation, the 3 form over here goes into lower dimensional 3 form plus lower dimensional 2 form, which is written like that. Now you might wonder, why did I pick sort of the letters A, B, and C or something like that? Well, that's because at some level it's just notation. I could have used any letter I wanted to call these fields what they are. But the reason I use that notation is because now if I write down the fields G mu nu,